This webcast discusses how to complete the first lab report on tumble buggies. Okay, so we'll just go through. Much of this report has been completed in class together, but I'll just go over a few of the important points. First of all, you are the primary investigator, and so you want to put your name here. And then you also want to include the full names of the other members of your team. I'm just making up names, so don't worry about that. Okay, so we've put your name as the primary investigator and your team's names. It is okay to make these black. You don't need to keep the blue font if you don't want to. Okay, so in class we recorded observations of what we saw when we watched the tumble buggies moving across the floor. We also completed this table in class about what we would measure and how we would measure it. And the purpose and the identification of the independent and dependent variables was done in class. But let's talk about the constants. So I believe we did this in class, but we'll go through this again. Please be sure that you give a specific value for each one of these constants. For example, don't just say that the buggy always started from the same initial position. Instead, we need to say what that initial position was. In my example, I'm saying that the buggy was always started at position 400 centimeters. Be sure that you give the number of the buggy that you used for your team. Okay, so I'm going to use the example of buggy number 3. And in my example, the buggy moved in the negative direction, meaning it started at a high position, 400 centimeters, and came back towards 0. All of the test apparatus, the meter stick layout, stopwatches, etc., was the same for every run. The buggy always moved on the same type of surface, and we had the same team members performing their roles. We didn't switch that up. Okay, so we've described that. Then there will come our data table. Now my data table does not have numbers in it, and yours would. So, but we want to have, your numbers here and the calculated position. At the bottom of the table, there is a sample calculation, and I have put something in here so that you have a formula block that you could edit if you'd like to, but you need to make sure that this is for your data, okay? And so we're using the time of 2 seconds. That should be your top row of your table, and we're going to add up the 5 positions that were measured, and then we're going to calculate the average. And so I would come in here, and if these, your numbers may be different, I would calculate, and I would put in my exact numbers here, divide by 5, and then I would type the calculated average here. It does not calculate for you, but please make sure that you update this sample calculation at the bottom of your table. After the table, there's going to be a page where you paste in a picture of your graph. We do not want to leave this blue text that is telling you what goes on this page. Instead, we want to put the actual picture itself. So I'm going to go to a view. Let's see here. Yeah, now I can do it. I'm going to view multiple pages so that you can see. I have my first page with the observations, my second page with the constants, my third page with the data table and the sample calculation, and then my fourth page here has the picture of my graph. Now we did these graphs by hand on a piece of paper, so I've taken a photo of it and pasted that photo in the report. Okay, then below that is the place for the analysis, and here's where I'm calculating the slope of my graph. Notice in my example I have a negative slope because I'm going in the negative direction, and so I have taken these 2 points. I've labeled the coordinates of these 2 points identified by triangles because those are the 2 points that I'm using to calculate the slope. Okay, they are not my original data points. And then, let's see, and I do have the physics equation. And again, we did this in class, but just make sure that you have the calculation of your slope with the units, the y-intercept with the units, identify the variables and the descriptive names. X and T are the descriptive names of those variables, and then here is the physics equation. And I'm following all the rules of the physics equation. I've put parentheses around the slope. I have the slope with units identified and also units on the y-intercept. Okay, and then we get to the conclusions, and the first thing we want to do is to restate the purpose of the lab. You can copy that from up above on the first page, but make it into a nice sentence. Notice that my conclusions are double spaced. If you don't know how to do that, highlight the text and come up here to this type of icon and choose 2. We want to double space conclusions always. Okay, the second paragraph is a concise statement about what we found in our experiment. So I'm being very specific and clear. So I'm saying Buggy 3, and let's see, I have 2 words here. Buggy 3 started at position 400 centimeters and moved in the negative direction. Now this is my example. Yours may have had a different starting position and may have moved in the other direction. I explained that the graph of the position versus time was linear, and here is the physics equation. Notice that I hit a return so that I can put that physics equation centered on its own line. It's very important that the equation stand out. That is the star of the conclusions. It's the thing that people want to be able to see very easily. Okay, this is still part of the same paragraph, so I didn't indent, but I want to explain what the slope means. This minus 30 centimeters per second means that for every additional second that the buggy was moving, its position decreased by 30 centimeters. And then here we have a clear meaning of the y-intercept, so let's explain it. The y-intercept of 400 centimeters was the initial position of the buggy at time 0. Okay, and then here's a very important, we're just going ahead and giving our conclusions. Because the graph of position versus time was linear, the slope was constant. Therefore, Buggy 3 moved at a constant velocity. Now, in a lab report, we also want to think about what were the sources of error in our experiment. Every time we measure something, there are some types of measurement error, and so we want to think about those so that if we were to repeat this experiment, we might be able to improve on them. And so one way to do that is what I've done here, where I start by saying, well, there were several sources of measurement error in the experiment, which might be improved when the experiment is replicated. The most important sources of error are as follows. And in each one of these bulleted paragraphs, I want to describe the error. I want to try to quantify it, give a specific amount of it, and then also identify one or two methods to improve it. So, for example, there was a human reaction time error when using a stopwatch to measure how long the buggy is moving. I'm still describing the error. Team members need a bit of time to respond to the commands of starting and stopping the buggy. Okay, so in this next sentence, I'm quantifying that error. It's estimated that this error may be as large as 0.25 seconds, and that means the buggy position might be off by as much as plus or minus 10 centimeters. It's plus or minus because I could measure a time I could let it go too long, or I could stop it too soon. The 10 centimeters came from, since my slope here is 30 centimeters per second, if we were off by a quarter of a second, then that would actually be maybe 7.5. I guess I've rounded up here, but it could be off as much as this many centimeters. Okay, so we've quantified it, and now we want to talk about how could we reduce that error. And it says, due to the types of equipment available in our lab, we have limited options for minimizing this error. One is that a timer could be set to go off when the time interval is finished, and the other is that the person acting as the timer could be announcing the time as each second passes, and that would help the person who's going to stop the buggy to anticipate when it's time to stop. Okay, so we want to do that type of description of at least 2 types of error, and then that is all that we need in this lab report.